Hello students, welcome to Shri Classes. We'll start a new chapter, that is chapter number 4, Carbon and its Compounds in Science. Let us have a look at the chapter flow first. This is according to the current syllabus, and this portion is the deleted portion for this current year. So according to the revised syllabus, this is the current portion: bonding in carbon, versatile nature of carbon, and one more is the homologous series. These things have been included. Once again, if you look at bonding in carbon, versatile nature of carbon, under the versatile nature you have 4.2.1, 2, 3, 4 sections and 5 sections. Actually, in this fifth section, nomenclature of carbon compounds, many things have been deleted, but it is very difficult without the study of nomenclature of carbon compounds. It is very difficult to understand the homologous series at all, and therefore we will have to study the minimum required nomenclature of carbon compounds. What is the deleted portion? Chemical properties of carbon compounds, that is combustion property, oxidation, addition reactions and substitution reactions, all these have been deleted. And also important carbon compounds such as ethanol and ethanoic acid also removed, and the properties of ethanol, properties of ethanoic acid, that is also removed. Soaps and detergents. So this is the deleted portion, and we will be concentrating this year only on this portion. So let us begin the chapter now. Let us study what is the importance of carbon here. First of all, have a look at the PPT. Importance of carbon. Carbon is an element which plays a very important role in our lives, because this is the most important or one of the important constituents of these products. What are these products? All these products we use in our daily lives. For example, foods, starch, sugar, fats, vitamins, proteins, all these are made up of carbon. Carbon is one of the important constituting elements of these foods. Fuels like wood, coal, alcohol, petrol, all these are made up of carbon, or the fuels are also carbon compounds. Household and commercial articles such as paper, soap, cosmetics, oils, paints, all these are carbon compounds. Textile fabrics such as cotton, wool, linen, these are also carbon compounds. Of course, in drugs such as penicillin, aspirin, etc., these are made up of carbon compounds. Perfumes are also carbon compounds. Explosives, dyes, etc. So all these are the items that we use in our everyday life, and carbon being one of the most important constituents of these elements, carbon plays a very important role in our daily lives. So let us continue with the next one. See, you have to make a short notes also out of this. It is very important to make a short notes and write them properly. Next is natural abundance in nature. Natural abundance means availability of carbon in the form of different isotopes in the nature. That is called natural abundance. Now, if you look at the Earth's crust, it contains only 0.02% carbon. That is also in the form of carbonates, hydrogen carbonates, coal and petroleum. Carbonates, hydrogen carbonates, coal and petroleum, all these are in the combined forms basically. And also in atmosphere, it is available in the combined form, and the percentage is very less than or almost equal to 0.03%, you can say, and that is also in the combined form CO2. So abundancy or the natural abundance of carbon in nature is very, very less, 0.02% in the Earth's crust and 0.03% in the atmosphere. But still, as it plays a very important role in forming as one of the important constituents of many day-to-day items or many day-to-day usage compounds, carbon forms nearly 3 million plus compounds. So far, the scientists have identified nearly more than 3 million compounds. 3 million means 30 lakh compounds. That means you can see the importance of carbon. No other element in the periodic table can have such a large usage other than the carbon. Next, let us see what is chemical bonding. The meaning of bonding is the electrostatic force of attraction between the two atoms. So, chemical bonding in carbon we are going to study now, but mainly there are two types of chemical bonding, that is the force with which the two atoms or the elements are bound together. There are two kinds of binding in that. For your standard 10th standard we will study only two types. There are about 4-5 types, like apart from electrovalent bond and covalent bond, you have hydrogen bonding, you have coordinate bond, etc. But we are not going to study all those. According to your syllabus, the chemical bonding that we are going to study are mainly two types: electrovalent bond or ionic bond, which you have already studied, and in this chapter we are going to study the covalent bond. What is electrovalent bond or ionic bond? It is also termed as ionic bond. The chemical bond formed by exchange of electrons, that is either loss of electrons or gain of electrons, is called electrovalent bond or ionic bond. Here, between the two atoms, the exchange of electrons take place and the formation of new compound takes place by joining of two or more atoms. And the compounds formed by electrovalent bonds are called electrovalent compounds. Examples, you can remember these examples very easily. Generally, ionic compounds are compounds formed by metals and non-metals, such as salts, basically sodium chloride, calcium chloride, magnesium chloride. We have already seen the formation of all these compounds by electron dot structure, isn't it? Okay, next is covalent bond. What is covalent bond? This is totally different from electrovalent bond. Covalent bond, the bond formed by sharing of electrons is called a covalent bond, and the compounds so formed are called covalent compounds. In electrovalent bond, we see the exchange of electrons between the atoms or between the elements. Here, it is not the exchange of electrons. It is basically the sharing of electrons. Sharing of electrons takes place in order to form a chemical bond between given two atoms or two elements. And how this sharing takes place, we are going to study the electronic dot structure, that is Lewis dot structure for formation of covalent bonds. And what are the properties? Some properties of covalent bonds also we will see now. Examples for covalent bonds are formation of hydrogen chloride, water, ammonia molecule. If you look at this and this, the difference is covalent bonds are generally observed in non-metallic compounds. Here hydrogen and chlorine both are non-metal, hydrogen, oxygen non-metal, nitrogen, hydrogen non-metal. So we can observe the covalent bond formation in non-metallic compounds, whereas in metallic and non-metallic compounds put together you can observe the electrovalent bonds. Is it clear? So examples for covalent bonds are HCl, H2O, NH3, where the chemical bond is formed by means of sharing electrons but not exchange of electrons, whereas in ionic bond it is the bonds are formed by exchange of electrons. So we'll see some examples also for these two. First, make a note of this one. Next, bonding in carbon. Those covalent bond formation we'll see later. Okay, first let us see a little bit more. Let us have some more information about the carbon and its what is the reactivity of an element, and with respect to carbon what is reactivity, and why carbon cannot form the ionic bond. Once after understanding why carbon cannot form an ionic bond, then we'll go to once again covalent bond formation by carbon and some examples we'll take. Now, bonding in carbon, to study that, carbon is a tetravalent element. How do you say that it is a tetravalent? Tetravalency means, tetra means 4. The valency of the carbon is 4. Atomic number of carbon is 6. We represent carbon as 6C12, isn't it? Where 6 represents the atomic number and 12 represents atomic mass number. So atomic number for carbon Z equals 6, total number of electrons is equal to 6, electronic configuration is 2, 4. In K shell you have 2 electrons and in L shell you have 4 electrons. And therefore, how do you get the valency? Valency of this carbon element is equal to 8 minus 4, which is 4. And therefore, this carbon is called a tetravalent element. What is the position of the carbon in periodic table? Look at the electronic configuration 2, 4. So the number of shells indicate the period number. Here there are 2 shells K and L, hence the period number is 2. It belongs to P2 here, the period number 2 or the second period. Valence electrons 4 and therefore the group number is 10 plus 4, 14, and hence it belongs to group 14. It is very clear, I think. Next, what do you mean by the reactivity of an element? In a periodic table, if you look at all the elements are electrically neutral, meaning the number of protons and electrons are equal. What is the meaning of that one? The magnitude of positive charge is equal to the magnitude of negative charge. So electrically they are neutral. What about chemically? Chemically, other than the noble gases, most of the elements are highly reactive. Of course, reactivity depends upon element to element. What I can say is, most of the elements apart from the noble gases and nitrogen, etc., most of the elements are reactive in nature. So what do you define? How do you define that reactivity? So reactivity of an element, the tendency of an element to achieve a completely filled outermost shell either by duplet rule or by octet rule to attain the nearest noble gas configuration is called its reactivity. So noble gases are non-reactive, isn't it? Because they have outermost shell is completely filled by 8 electrons. If it is filled up with 8 electrons, it is called the elements are chemically stable by octet rule. When do you say the elements are chemically stable by duplet rule? If there is a K shell, which is an outermost shell, and if it is completely filled with 2 electrons, because K shell can hold up to at most maximum 2 electrons. The number of electrons in each shell is given by 2n square formula, where n represents energy level index number. For K it is 1, and therefore 2 into 1 the whole square is 2 electrons. So what is the reactivity of an element? Any element that you look at periodic table apart from the noble gases and few more elements, every element would like to achieve chemical stability either by octet rule or by duplet rule. Octet rule means by completely filling its outermost shell with 8 electrons, and duplet rule means completely filling its K shell with 2 electrons. I think this you have understood. So that is called the reactivity of an element. If the same concept is applied to the carbon, then carbon can take 4 electrons from the neighboring atom and it should form carbon anion, or it can lose 4 electrons and it can form cation 4 plus, isn't it? These are the two options to make it chemically stable. But is this possible really? Can carbon really gain 4 electrons? Is it possible? Or can carbon lose 4 electrons and become chemically stable by duplet rule? Is it possible? So let us have a look at those options now. So we'll understand that concept by means of a question here, which can appear in the exams also. What is the question here? Why carbon cannot form bonding with other atoms, with itself or with other atoms, by exchange of electrons, that is either by loss of electrons or gain of electrons? Listen carefully and read carefully the PPT, very important. To achieve nearest noble gas configuration, carbon has to gain 4 electrons or lose 4 electrons, because valence electrons are 4 here. First case, gain of electrons to form C4 minus anion. If it gains 4 electrons, the outermost shell, that is L shell, will have completely filled 8 electrons. So in that case, by gaining, carbon should suppose to form C4 minus anion. Is it not? Because 4 minus indicates it has to gain 4 electrons and become negatively charged ion, and that is called anion. And how many electrons it can gain? 4, and therefore C4 minus represents carbon anion. So the gain of electrons to form C4 minus anion, is it possible? Let us see. The nucleus has 6 protons because atomic number of carbon is 6. The nucleus has 6 protons, and it is very difficult to hold 10 electrons in place. How this 10 electrons has come? If the carbon gains additional 4 electrons from the neighboring atoms, 4 plus 4, 8 electrons in the valence shell plus 2 electrons in the penultimate shell or just before the valence shell. So 4 plus 4, 8 plus 2, 10 electrons. These 10 electrons are to be held in position by 6 protons which are present in the nucleus, and protons are positively charged species, whereas electrons, 10 electrons, are in the outermost shell. It is very difficult for 6 protons to hold 10 electrons in position because the force of attraction is not enough. So I'll read this part once again. Gain of electrons to form C4 minus anion. The nucleus has 6 protons and it is difficult to hold 10 electrons, that is 4 electrons in position. Hence the carbon cannot gain 4 electrons. The reason is very clear. Carbon cannot gain 4 electrons and form an ionic bond. Now in that case, is it possible for carbon to lose 4 electrons, and by duplet rule can it achieve stability? Let us see once again. It could lose 4 electrons to form C4 plus cation. When it loses 4 electrons, it becomes a cation, which is a positive ion represented by C4 plus cation. Now what is the difficulty in formation of this case? It requires large amount of energy to remove 4 electrons, leaving behind 6 protons to hold only 2 electrons. See here, K shell 2 electrons, L shell 4 electrons. In the center of the nucleus or in the nucleus we have 6 protons. It requires enormous amount of energy to remove these 4 electrons from the valence shell, and 6 protons should hold only 2 electrons in that case. First of all, the energy requirement is so high that it is not possible to remove 4 electrons. You got it? And there are 6 protons. Can those 6 protons hold only 2 electrons in place? That's also a question. And therefore, it could lose 4 electrons to form C4 plus cation. It requires a large amount of energy to remove 4 electrons, and hence it is not possible for carbon to lose 4 electrons and form once again ionic bond. So it requires large amount of energy to remove 4 electrons, leaving behind 6 protons to hold only 2 electrons in position, and therefore this is also not possible. So when carbon can neither gain 4 electrons and form compounds or can lose 4 electrons and form compounds, in that case how does carbon form compounds with itself or maybe with other atoms such as hydrogen, oxygen, nitrogen, fluorine, and halogens, basically fluorine, chlorine, bromine, etc. How does carbon forms the bonding? In order to overcome this problem, see here, therefore carbon cannot form electrovalent bonds with other atoms. That is very clear. And what is the bonding in carbon? To overcome above problems, carbon forms bonding with itself and with other atoms by sharing of electrons, and thus forming covalent bonds and hence covalent compounds. Is it very clear? So what is the nature of bonds formed by the carbon with itself as well as with neighboring atoms? Carbon can share its 4 valence electrons with the neighboring atoms and it can form a covalent bonds. Is it clear? And these valencies, the 4 electrons can be compared with 4 arms. there are 4 arms for the carbon, something like this, 4 arms for the carbon, and it can hold 4 neighboring atoms, and therefore it can form the covalent compounds and the covalent bonds by sharing of the electrons. Okay, so I think this is very clear for all of you. And most important question, why carbon cannot form bonding with other atoms by exchange of electrons? To answer this, these are the 2 reasons, and hence the bonding in carbon is covalent bonding, and it forms the covalent compounds. Hope this slide it is very clear for all of you. Next, here let us have the comparison of ionic and covalent compounds. Ionic compounds, covalent compounds. Ionic compounds are formed by loss or gain of electrons, whereas covalent compounds are formed by sharing of electrons. This is very clear. Generally, ionic compounds bond strength is very high. That means the electrostatic force of attraction that binds the 2 atoms is high. So in order to break open those bonds, definitely we have to supply more energy, and therefore they have more high melting point or boiling point. What is the reason? They have a strong bond and there is a more force of attraction between the atoms or molecules. Hence, they have ionic bonds, ionic compounds have higher MPBP, whereas for covalent compounds generally have low MPBP, low melting point and boiling point, because of weak bonds and less force of attraction. If you look at some of the compounds which are the covalent compounds here, which have been given covalent compounds, acetic acid, chloroform, ethanol, methane, all these are covalent compounds. What is their MPBP? These units are here Kelvin, 290 Kelvin, 391 Kelvin, 209, 334, 156, 351. If you look at the melting point here, this is 290 Kelvin. So degree Celsius, how do you convert it? Degree Celsius is equal to, you have to subtract minus 273, isn't it? So if I take 290 Kelvin minus 273 gives me 17 degrees Celsius. That means acetic acid melting point is 17 degrees Celsius. Acetic acid, of course, see in winter season and all, acetic acid will become solidified, and therefore it is also called, pure acetic acid is also called glacier acetic acid, and melting point is 70 degrees Celsius, and boiling point is 391. So 391 minus 273, which is 118 degrees Celsius. So if you look at all this, generally the melting point and boiling point of the compounds which are covalent compounds is less. And what else? Next is, here you have point C, conducts electricity, conduction of electricity. Ionic compounds conduct electricity in aqueous or molten state as they dissociate into ions. See, conduction of electricity, generally in solids, the electricity is conducted by means of flow of electrons. What about in compounds? There are no free electrons which are available in compounds, but when the compounds are in the fluid state, either in the molten or in the form of aqueous, that is in the liquid phase, and if they have ions, then the ions conduct electricity. So for ionic compounds, they conduct electricity only in aqueous or molten state, because the compounds dissociate into ions, and the physical movement of ions are responsible for conduction of electricity, whereas most of the compounds do not conduct electricity in case of covalent compounds, because they do not dissociate into ions. For example, we have already seen an experiment, that is alcohol or glucose solution. It will not conduct electricity because the compounds will not dissociate into ions in aqueous state, and ions are responsible for conduction of electricity, and therefore covalent compounds do not conduct electricity, whereas ionic compounds conduct electricity in aqueous or molten state. So this is one part so far which we have seen. Now let us understand the types of covalent bonds. First, make a note of this one. and then we'll go for types of covalent bonds. Now, the types of covalent bonds, there are mainly three types: single covalent bond, double covalent bond, and triple covalent bond. What are these bonds and how to represent the Lewis dot structure and the bond structure for these three different types of compounds we'll see. Single covalent bond. This bond is formed by sharing of one pair of electrons. Remember, single covalent bond. Covalent bond means sharing of electrons. Single means one pair of electrons are shared between atoms. In that case, the bond formed is called a single covalent bond. So, single covalent bond is formed by sharing of one pair of electrons. Remember, one pair of electrons. It is one pair of electrons. What are the examples for this? Formation of hydrogen molecule, chlorine molecule. These two are diatomic molecules. Hydrogen fluoride, water, methane, etc. These are the examples for formation of single covalent bonds. If you look at the formation of hydrogen, hydrogen has only one electron in the outermost shell. K shell is the outermost shell and one electron. And how the hydrogen is formed? Two hydrogen atoms having one electron each, they will merge together, and this hydrogen will share its electron with this hydrogen with this electron. So finally, when these two hydrogen combine together, this is the shared region. You find two electrons, one electron of this hydrogen and another electron of this hydrogen. Here there are two electrons. So if I count now the number of electrons in K shell for this hydrogen, 1, 2. For this hydrogen in K shell, 1, 2. That means after sharing of electrons, if you check individually the atoms and the number of electrons in the valence shell, then the valence shell will be completely filled. Here K shell can have maximum of 2 electrons, and therefore for this hydrogen 1, 2, there are 2 electrons, one its own and another shared by the other electron. So if I count for this hydrogen the number of electrons in the valence shell, 2. In that case, this hydrogen is chemically stable, or this hydrogen has achieved chemical stability by means of duplet rule. Similarly, if I look at this hydrogen, this has its own one electron and another electron shared by this hydrogen. So this hydrogen also has achieved chemical stability by duplet rule. So individually when you count, for individual atoms, if we count the total number of electrons, you have to take into account the shared number of electrons also by the other atoms. In that case, definitely the valence shell should be completely filled either with 2 electrons or with 8 electrons. Here hydrogen molecule is formed by a duplet rule, that is by sharing of electrons, and hence formation of hydrogen molecule, which is a diatomic molecule, is by formation of covalent bonds, and this particular structure is called a Lewis dot structure. What is Lewis dot structure? Generally, Lewis dot structure represents valence electrons around the atom represented symmetrically, but here we are showing the formation of the molecules by means of Lewis dot structures, which involves only the valence electrons. What is a bond structure? There is one more structure representation, that is called a bond structure. Here you can see H, one line here, that is called a bond, and this is H here. So if I represent H hyphen H, that hyphen or one straight line represents a bond. So this is a bond structure and this is a Lewis dot structure. I hope you are able to understand. Our camera can be brought here to the front, and then I can explain that. To represent this one, hydrogen, here you can see this is a Lewis dot structure, whereas here this part H hyphen H, this is called the bond structure, this is called the Lewis dot structure, and this is called the bond structure. That means one bond or one line represents one pair of shared electrons. one pair of shared electrons. Is it clear? Fine. So you come, I think it is very clear for you how to represent the formation of single covalent bond with an example of hydrogen. You can try with chlorine, hydrogen fluoride, water, CH4, etc. Here one more diagram is given here as formation of methane molecule by single covalent bond. So I think it is better if I can explain this on the board. Let me try to explain the formation of methane, the electron dot structure as well as bond structure on the board. Now we know that carbon has 4 electrons in the valence shell because 6C electronic configuration of carbon is 2, 4. So Lewis dot structure is something like this. Carbon has 4 electrons. What about hydrogen? Hydrogen has only 1 electron in the valence shell. So now how many carbon can link with 4 hydrogen atoms, because this electron is shared with the carbon electron to form one covalent bond, single covalent bond with hydrogen. So how many such hydrogens are required? Definitely 4 hydrogens are required. So we can represent something like this. If this is a carbon over here, let us have 1 hydrogen there, here and here and here. Here this is hydrogen, hydrogen, hydrogen and hydrogen. Now the valence electrons of carbon can be represented by cross, whereas hydrogen by dot, because cross represents the electrons of carbon, dot represents the electron of hydrogen. So one pair is shared. The hydrogen shares its electron with 1 electron of carbon. Similarly, this hydrogen is having 1 dot and 1 cross of carbon. Here also 1 dot of hydrogen and 1 cross of carbon. 1 dot of hydrogen and 1 cross of carbon. So this is called the Lewis electron dot structure, which represents covalent bond formation, that is also single covalent bond formation between the carbon atom and hydrogen atom. It is called a single covalent bond because if you look at the shared region, all these are the shared region. This one and this one and this one and this one is a shared region. If you look at the shared region, you have 2 electrons, here also 2, here also 2, here also 2. Now whether hydrogen has achieved its chemical stability, let us have a look at this. Hydrogen has got only 1 shell, K shell, that is also an outermost shell. Has it got 2 electrons? Count it. In the shared region, count it. 1, 2. Yes, hydrogen is chemically stable now because of 2 electrons in its outermost shell, that is K shell. So hydrogen has achieved chemical stability by duplet rule. Here, yes, hydrogen has achieved chemical stability by duplet rule. Here same thing, here same thing. So one carbon atom can link with 4 neighboring atoms because of its tetravalency, and the 4 hydrogens are represented, and in all the 4 cases here hydrogen has achieved chemical stability by means of a duplet rule. Fine. Has carbon achieved chemical stability? Let us count the valence electrons. That means a shared pair of electrons need to be counted. If the total number of electrons are 8, then I can also say carbon has achieved chemical stability by octet rule. Let us count for carbon 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons in its valence shell. How it is possible? Because carbon got shared electrons from hydrogen element, and therefore when I count the total number of electrons pertaining to carbon atom, I need to consider the shared pair of electrons also, or the shared number of electrons also, and therefore total number of electrons with respect to carbon, if I count 2 plus 2 plus 2 plus 2, 8 electrons. So carbon has also achieved its chemical stability by means of octet rule. I hope this is very clear for all of you. Now this is called Lewis dot structure. LEWIS, Lewis dot structure, where only the valence electrons are represented in formation of the chemical bonding by means of these circles. Now, this is equal to one more structure called bond structure. What is this bond structure represents? Bond structures are represented by one line here, one bond formation. One line represents one bond, and one bond represents one pair of shared electrons. One pair of shared electrons. And therefore, in order to represent this methane molecule, this is methane molecule, CH4 is the molecular formula for this one. So in order to represent this one, let carbon be here. Each shared pair of electrons is represented by one bond, like this line. So this one is represented as this way, and this one this way, this way, and this way. Put hydrogen everywhere here, and this is called the bond structure. I hope you have clearly understood what is the difference between the Lewis dot structure for formation of covalent bond formation. Here in this case it is a single covalent bond formation, and the same for bond formation, that is a dot structure bond formation, is represented by a bond structure. This is a bond structure, and this is a dot structure that represents formation of methane molecule. So these are the example for single covalent bond. So make a note of this one. Now let us have a look at single covalent bond formation in chlorine, hydrogen fluoride, and water molecule. Now, in order to do so, first of all we should know the atomic number of each element, electronic configuration, and then we should know the valence electrons. So chlorine atomic number is 17, and electronic number of electrons also 17. And what is electronic configuration? 2, 8, 7. So 7 electrons are there in the valence shell, K, L, M, in the M shell. So this is the Lewis dot structure for individual atom. How many electrons are there? 7. 1, 2, 3, 4, 5, 6, 7. Here also 7. How the bond formation takes place between these two? This chlorine atom will share its electron with this chlorine to form a single covalent bond. So the formation of chlorine can be shown as, this is how the Lewis dot structure can be represented. Cl and Cl. These are a shared pair of electrons. One electron, whichever is over here, it is represented in this shared region, and this electron of this chlorine atom is also represented in this shared region, meaning the electron of this chlorine is shared with this electron of this chlorine. So the bond formation, single covalent bond formation, takes place by sharing of one pair of electrons between two chlorine atoms to form a diatomic chlorine molecule. So also I have to represent the non-shared electrons also. These are called shared pair of electrons, and also these are called bond pair electrons. These are also called bond pair electrons. I hope you are able to see very clearly whatever I am writing. Bond pair electrons. So the remaining electrons need to be represented over here. If one electron is shared with this one, the remaining 1, 2, 3, 4, 5, 6 have to represent like this. बराबर आ गया समझ में? Here also these are these electrons, whereas the bond formation takes place between these two electrons. This is chlorine molecule formation. This is a dot structure, Lewis dot structure. What about bond structure? This simply you can represent like this: chlorine single bond with chlorine. And it is preferable to represent the lone pair electrons also, or non-shared pair of electrons. This is a shared pair, all these are lone pair electrons, or bond pair electrons, lone pair electrons, you can say like that. Here this is a bond structure. Sometimes we may not show these electrons. Okay, it's okay. Simply you can like this also you can write Cl, Cl. This is also acceptable. Okay. Now what else is to be taught in this? That's all. Next, hydrogen fluoride. Fluorine belongs to group 17 and therefore its valence electrons 7. Rather than atomic number, another concept of writing valence electronic configuration is to which group of fluorine belongs to. It belongs to halogens. Halogens is group 17 and 17 minus 10 gives you 7. So the valence electrons of fluorine 7 and therefore I have represented all those 7 electrons as 1, 2, 3, 4, 5, 6, 7. Now it can form a bond with hydrogen, that is single covalent bond, by sharing its one electron with sharing of another electron of hydrogen. So this is how the bond formation, Lewis-Strauss structure, I can represent it. Hydrogen here and fluorine, one cross and one dot of, dot is an electron belonging to hydrogen atom and crosses represent valence electrons belonging to fluorine atom. So hydrogen shares its one electron with one electron of fluorine. Now you count for hydrogen these two electrons. Hydrogen achieved chemical stability by attaining the nearest noble gas configuration of helium, that is by duplet rule. Whereas fluorine, let us represent the other electrons and then count it. Okay, now for fluorine, total number of electrons are 1, 2, 3, 4, 5, 6 and the shared pair 7, 8. Fluorine achieved chemical stability by attaining by octet rule, you can say. It has achieved chemical stability by octet rule, that is by completely filling its valence shell by 8 electrons. Here also you can count for this chlorine atom total number of electrons 1, 2, 3, 4, 5, 6 and the shared pair 7, 8. For this chlorine 1, 2, 3, 4, 5, 6, 7, 8. So chemical stability is achieved by chlorine atom by octet rule. Now let us have a look at water molecule. Hydrogen and oxygen. Oxygen belongs to, what is the atomic number of oxygen? Atomic number for oxygen, it is 8. Electronic configuration 2, 6. Valence electrons 6, represented by crosses 1, 2, 3, 4, 5, 6. And hydrogen only one electron in each its valence shell. So the bond formation or the Lewis-Strauss structure can be represented as here oxygen, one big circle and one circle for this hydrogen and another circle for this hydrogen. So one dot and one cross of oxygen. Here also one dot of hydrogen and one cross of oxygen. Remaining electrons of oxygen can be represented like this, and this is hydrogen, this is hydrogen. Count the number of electrons for hydrogen 1, 2. By duplet rule it is achieved chemical stability. Here also this is achieved by duplet rule, the chemical stability. What about oxygen here? Count all the shared electrons 1, 2, 3, 4, 5, 6, 7, 8. Oxygen achieved chemical stability by means of octet rule. So this is a Lewis-Strauss structure and this is also a Lewis-Strauss structure. How to represent this one as a bond structure? Oxygen here, this is hydrogen here and this is hydrogen here. And there are two lone pairs like this, you have to represent it. So this is the bond structure. Also see, generally Lewis-Strauss structure, bond structure, you can also represent this to be specific. This becomes a bond structure because we are representing each bond by a line here which represents shared pair of electrons, and hence it is called a bond structure. Okay, so make a note of these three also. You may get these questions in the exams. Now let us have a look at double covalent bond. Covalent bond, sharing electrons. Double, two pairs of electrons are shared between the atoms or the elements. So double covalent bond is formed by sharing of two pairs of electrons. Examples: formation of oxygen molecule, ethene molecule, CO2 molecule. If I look at the oxygen, let us understand how it is formed. 8O, 8 represents atomic number of oxygen. Electronic configuration is 2, 6. There are 6 valence electrons represented by crosses here 1, 2, 3, 4, 5, 6, and another oxygen also will have 6 valence electrons. So these two are oxygen atoms. How can I combine this one? Here oxygen, these two electrons will be shared with these two electrons to form two pairs, there are 4 electrons which are shared, and therefore it forms 2 pairs of shared electrons, and thus it forms a double covalent bond. So oxygen and oxygen, these 2 electrons are shared with these 2 electrons which are represented in the shared region, and the remaining electrons are represented here. So totally 4 electrons, and therefore 2 pairs of electrons. Each pair is represented by 1 bond. There are 2 pairs here, therefore there are 2 bonds here. So this is a bond structure and this is a dot structure. Why do we represent with the 2 lines here? Because there are 2 pairs of electrons which are shared, and therefore 2 bonds are represented by 2 straight lines, and hence this is a bond structure and this is a Lewis dot structure. So formation of ethene, carbon dioxide anyway I have taken as an example which we will see. You can try formation of ethene molecule yourself. You try this. If I am not able to do so, I can discuss that in live session. Okay, fine. Next comes a triple covalent bond. This is a triple covalent bond. As the name suggests, if there are 3 pairs of shared electrons between the atoms, and then this is called a triple covalent bond. Okay, I think camera can be adjusted a little bit to include me also, or you can take a little bit this side. Okay, fine. Triple covalent bond, once again, it is formed by sharing of 3 pairs of electrons. What are the examples? Nitrogen is the best example, or ethyne molecule. See, ethene, ethyne, alkanes, alkenes, alkynes. After discussing those things, it is very easy to represent the Lewis dot structure as well as the bond structure for hydrocarbons such as ethene, ethine, etc. But for the time being, to understand the double covalent bond, single, double and triple covalent bond, you can take some other molecules such as oxygen molecule, nitrogen molecule, which are easier to understand also. Okay, no, it is not covering properly. This is lost here. Check it. Okay, now next. So what is triple covalent bond? When 3 pairs of electrons are shared between the elements, then it forms a triple covalent bond. Okay, now here you can have a look at this nitrogen molecule. Nitrogen atomic number is 7. Electronic, therefore total number of electrons also 7. Electronic configuration is 2, 5, and therefore there are 5 valence electrons in the outermost shell represented by crosses. Another atom, yes, 5 electrons. How do these 2 atoms will combine? These 3 electrons of this nitrogen atom will be shared with these 3 electrons of this nitrogen atom to form a triple covalent bond. 3 pairs are there. First pair, second pair, third pair. So 1, 2, 3. 3 pairs of shared electrons are there, and non-shared electrons, which are also called lone pair, are these 2 and these 2. Each shared pair is represented by 1 line called 1 bond. So 3 shared pairs and 3 bonds, and therefore between nitrogen you can find 3 lines here, and this is a bond structure and this is a dot structure. Example you can also take for ethine molecule. These structures, when I discuss the ethene and ethine, I'll try to explain. Remind me, I'll explain the formation of dot structure also and formation of bond structure also once again when I discuss alkanes, alkenes and alkynes, their general formula, etc. Okay, so this is how the formation of bond takes place by means of single covalent, double covalent or triple covalent bond between the molecules. Okay, so make a note of all these things. Here there is one in-text question. What would be the electron dot structure of carbon dioxide which has the formula of CO2? In order to draw all these electron dot structures, which are also called Lewis dot structure, dear students, make sure that you know all atomic numbers first. At least atomic number you must remember. Based on the atomic number, number of electrons. Based on the number of electrons, electronic configuration. Based on the electronic configuration, valence electrons can be identified, and valence electrons need to be represented in the Lewis dot structure. Is it not? So, what is the electron dot structure, which is also called the Lewis dot structure for CO2? Carbon is a tetravalent, so carbon is represented at the center. And oxygen, there are 2 oxygen atoms taken, and let us represent the electrons now. For carbon, the electrons are represented by dots here, and for oxygen, the electrons are represented by crosses. Valence electrons for carbon 4, so 1, 2, 3, 4. Valence electrons for oxygen 6, 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. But when you draw the circles, the shared pair should be represented within the intersected circles. So this indicates the shared pair and this indicates the shared pairs. Now 2 electrons of oxygen are shared with 2 electrons of carbon to form double covalent bond here, and here also a double covalent bond. And therefore, if I want to represent the bond structure between C and oxygen, 1 line, 2 line, there are 2 lines here. For this side also there are 2 lines, means carbon forms a double covalent bond with oxygen, isn't it? So this is the bond structure and this is the Lewis-Strauss structure. Important in the bond structure, if you represent the lone pair electrons also. Lone pair means which are not the bond pair, which are non-shared. Bond pair means shared pair of electrons. Lone pair means non-shared electrons. So if you represent lone pair also, it is preferable. So this is a bond structure and this is a dot structure for CO2. I hope you understand this clearly. Next. Sulfur 8 molecule. In text question, what would be the electron dot structure of a molecule of sulfur which is made up of 8 electrons of atoms of sulfur? The 8 atoms of sulfur are joined together in the form of a ring. It forms a ring structure. So this I'll discuss formation of sulfur molecule which involves 8 atoms on the board. For sulfur, what is the atomic number? 16. Number of electrons? 2, 16. Electronic configuration? 2, 8, 6. And therefore, there are 6 electrons in the valence shell. If I take, okay, let us represent those 6 electrons as 1, 2, 3, 4 and 5 here, 6 here I'll represent. Let me take one more sulfur atom here. 1, 2, 3, 4, 5, 6. One more. 1, 2, 3, 4, 5, 6. One more sulfur. 1, 2, 3, 4, 5, 6. One more sulfur. 1, I hope you are able to understand what I am drawing here. देख लो एक बार. Five, 6. Everywhere did you find 6 electrons? Everywhere? Yes. How the bond formation takes place? These two are shared. These two are shared. These two are shared. These two are shared. And here, 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 and here. So this is the bond formation. In terms of, this is for understanding only. Now the same is can be represented like this. How many atoms? 1, 2, 3, 4, 5, 6, 7, 8. One circle and another circle. Here I require one more. Here I require one more. 1, 2, 3, 4. Then I require here one more. Here one more. 1, 2, 3, 4, 5, 6. Another 2. 7, 8. 7, 8. So we have found a ring here. Let us represent sulfur everywhere. Yes, yes. Yeah, yes. From this you can conclude everywhere the bond formation is single covalent bond. One pair of electrons are shared, and therefore everywhere I'll represent one pair. Correct? From this you can see everywhere number of shared pair electrons are one pair, isn't it? Here also. Now remaining electrons, see, if I consider this sulfur atom, 2 over here and 2 over here, 2 have been shared, another 4 are remaining, isn't it? 1 is shared here, 1 is shared here, 4 are remaining. Count whether 8 electrons are there. 1, 2, 3, 4, 5, 6, 7, 8. Counting should take into account the shared electrons also. So 8 electrons. For this now, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. For this, 1, 2, 3, 4, 5, 6, 7, 8. So sulfur has achieved chemical stability by means of octet rule, and it is S8 molecule. Sulfur molecule is S8. This is the formula of sulfur molecule. You got it? So this is the structure of S8, and this is called a Lewis dot structure. This is Lewis dot structure. What is the bond structure? This, instead of these circles, I'll represent it by a bond. I can represent something like this also. That's all. 1, 2, 3, 4, 5, 6, 7, 8. Sometimes we represent as a crown structure, but it's okay. You can represent a ring structure also. So this is a Lewis dot structure, and this is a bond structure. Non-paired, that is lone pair electrons also you can show here. Something like this. You can show that. If we show it is better, otherwise also it's okay. This is how you can show it. So I hope you have understood the formation of S8 molecule. So let's get back to the PPT now. So in text question, what would be the electron dot structure of a molecule of sulfur which is made up of 8 atoms of sulfur? Hint, the 8 atoms of the sulfur are joined together in the form of a ring. So this is the electron dot structure, and this is a bond structure. Details have been given. Please make a note. Now, so far the basics of carbon element, and basically the bond formation is what we concentrated. Single covalent bond, double covalent bond, triple covalent bond, and with examples how to represent the bond formation in terms of Lewis dot structure and the bond structure we have understood. So let us end the lecture over here. In my next lecture, we will be taking most important aspects, that is the isotopes of carbon and allotropes of carbon, and its some unique ability or unique nature of carbon also we are going to study in my next lecture. So for the time being, let us end the lecture over here and see you in the next session with the rest of the portions. Thank you very much for watching.